Hey everyone, welcome to another session of Ceerazzledazzle Physics. In this video guys, I'm going to be talking you through charge, spheres and Coulomb's law, and in the brackets, forces in equilibrium, yes? So this concept guys about charge, spheres and Coulomb's law incorporates your knowledge about forces in equilibrium. Okay, before we get going, make sure that you understand what Coulomb's law is before actually tackling this topic, because you need that knowledge in this unit. Right, so what exactly is Coulomb's law? Hopefully you can remember that Coulomb's law is going to be this. Let's say we have a charge of Q1 over here and it's positively charged, and we have Q2 over here, it is also positively charged. Right, surely you recognize that both of them will be experiencing a force, moving them away from each other, the repulsive force over here. Let's say they're also separated by a distance r. The force between them will be given by Coulomb's law. F is equal to 1 over 4 pi epsilon naught times by Q1, Q2 divided by r squared, where r is the distance between them. Yes, between there and there. If you don't like that, then we can put 1 over 4 pi epsilon naught as equal to k. You might not know what the constants are, so we'll just give you the constants. When you're doing the calculations for this, epsilon naught will be given by, it's going to be equal to 8.85, yes, 8.85 times by 10 to the minus 12, Fm minus 1 farads per meter, and also the value of k, when you're doing your calculations, you can simply remember it as 9 times by 10 to the power of 9. So that's going to be my value of k, 9 times by 10 to the power of 9 Newton meter squared divided by Coulomb squared. Yes, make sure you can see where those units come from. Okay, so hopefully you understand what Coulomb's law is, but now let's look at it in this example over here. Right, so let's say we have a beam. Yes, we have a beam over here and we hang a balloon from it. Yes, one balloon from it. We hang another balloon next to it. Okay, yeah, easy stuff. Yeah, two balloons over here. And let's say from here we would take that and we were to charge both the balloons with the same charge. So we were to add some negative charges onto this one. Okay, maybe static electricity, and then touch it on top and add some charges onto this one. Hopefully you recognize that both the balloons will move away from each other over here. So what happens is this balloon will move outwards right now, and this one will also move outwards. Don't forget they're being suspended by a piece of string. Right, so this is charged negative, this one is also charged negative over here. Hopefully you can see that we're going to incorporate Coulomb's law into this problem. So first of all, recognize that yes, the two balloons, this one will have a tension going along here. This one will also have a tension across here. The balloons themselves, or like you can talk about them being charged spheres, charged spheres over here. It will be the mass of the balloon and the times by gravity, so the weight will be acting on this one as well, and the same thing for this one over here, mg. But because the balloons are in equilibrium, so they're not moving, so they've moved apart, yes, there will also be a repulsive force between them. And obviously that repulsive force will be given by Coulomb's law, which we just looked at. So the force which is pushing outwards over here and the force pushing outwards over there, this force will be given by Coulomb's law. So F over here. So F, we're going to put Coulomb's force. So Coulomb's force over here. Yes, due to Coulomb. There we go. Okay, right, now from here, don't forget that because they're in equilibrium, we should recognize that the resultant force upon it will be equal to 0. Yes, for each of these balloons, the resultant force upon each one of them is going to be equal to 0. So make sure that you're aware of that. So now look, this topic will combine your knowledge about forces in equilibrium and Coulomb's law together. So we're going to combine both those different concepts to tackle some problems. Right, for me, the best way I like to teach this topic is by walking kids through a question. So let's do a very difficult question based upon this principle of combining Coulomb's law and forces in equilibrium. Okay, so here's the question. A student wants to test Coulomb's law, which is about the force between two charged objects. She plans to hang two balloons on insulated threads, charge them both with equal positive charges, and measure the angles at which they hang away from each other. The dimensions she plans to use in her experiments are shown in a diagram. So there we go, the two balloons over here. She thinks she can make an accurate measurement if the balloons hang at an angle of 1.5 degrees or more from the vertical. Add to the diagram to show that all the forces acting on one of the balloons. And then, hence, show that the minimum charge Q she needs to have on each balloon must be 0.1 microcoulombs, assuming that each ball behaves as though the charge were concentrated at its center. Okay, right, so first of all, let's do this. So we've got to do the first bit of the question in terms of the forces. So first of all, it's just one of the balloons, such as this one over here. Tension's pulling upwards. We know the weight is pulling downwards over here. but due to Coulomb's law, there's a repulsive force pushing outwards. This is the force. There we go. So we've done that right now. Okay, now we're trying to find the charge. How are we going to find the charge on those balloons? Well, it's quite difficult because there's multiple things in this problem. So we've got the length of the thread over here. We've got the distance between them when they're attached at the top. So let's look at Coulomb's law. We know that force due to Coulomb's law will be equal to K Q1 Q2 divided by R squared. K Q1 Q2 divided by R squared. The value of K, don't forget the value of K is going to be 9 times by 10 to the power of 9. Okay, right. It says in the question at the top they're equal positive charge. So Q1 is the same as Q2. They're both the same. Q1 is the same as Q2 in here. So the first thing we're going to say is that obviously both the Q's are the same. So K Q squared, because Q1 is equal to Q2, so they're both the same thing, divided by R squared is equal to F. Right. Don't forget, this F is this F here. There we go. Okay, now from here, let's just talk about this. Let's talk about the actual sphere itself. If we were to just draw that, I'm going to draw it out again over here. We notice that here is the sphere. We know that the weight of it is pulling down. It also has the force pulling it to the right, yes, which is the force due to Coulomb's law. There's a tension going upwards over here. But don't forget, because it's in equilibrium, the resultant force must be 0. So if I was to resolve it, let's just drop this over there, drop this over there. We know that this force must be equal to this force. They both must be the same in the horizontal plane, and the force upwards must be equal to the force downwards over here. So these two must be the same as well. Right, if you look at our diagram, don't forget this is 1.5 degrees, so this is 1.5 over here, 1.5. So let's resolve this component. This one will be hopefully t sine 1.5. It's t sine by 1.5 over there, and this one over here will be t cos open bracket 1.5. Yes, hopefully you can resolve those two forces. Yes, this is t sine 1.5, this is t cos 1.5 over here. Right, so now we're here. We know that the force pulling this way must be equal to this force there. So let's write that down. So horizontally, in the horizontal plane, we know that F is equal to T sine of the angle 1.5. Okay? And then obviously F is therefore KQ squared over R squared is equal to T sine of the angle 1.5. Right over here. Okay. But you might be thinking, hang on a minute, like we're no way closer to finding out Q. Yes, how are we going to find out Q? But we can find T, everyone, don't forget we can find T out. Because look, we know that the force pulling downwards is the weight, mg, that must be equal to the force upwards, T cos 1.5. So therefore we can also say in the vertical plane over here, in the vertical plane over here, we're going for, look, upwards forces and downwards forces. We can say that T cos of the angle 1.5 is equal to mg. Yes, and therefore T is equal to mg divided by cos open bracket 1.5. So T is equal to the mass 0.0018 times by 9.8 divided by cos open bracket 1.5 over here. So therefore T is equal to both of them. It's going to be equal to 0.0018 times by 9.8 divided by cos 1.5. My answer is going to be equal to the value of T is going to be 0.018 newtons. That's going to be my value of T pulling upwards over here. Right, so now don't forget, the whole question is asking us to prove that the charge, the minimum charge, Q on one of them, is 0.1 microcoulomb. So we're trying to find out Q. We've just found out T, we can now whack that into here. So we're closer now than before. So we can say that KQ squared divided by R squared is equal to 0.018 sine of the angle open bracket 1.5 over here. So let's do this, times by sine open bracket 1.5. The answer is going to be yes, we're getting the answer of 4.619 times by 10 to the minus 4. There we go. Is equal to KQ squared. Yes, KQ squared divided by R squared. KQ squared divided by R squared. Right, now, you might be thinking, hang on a minute, surely we could just rearrange it now. Don't forget, K is given to us in the question. K is 9 times by 10 to the power of 9. Yes, but we don't have R, so we've got to find out R. Look, in this problem, on purpose they made it challenging. R is the distance between the center of the sphere and this one over here. So it's this distance we're trying to find out. This is going to be the value of R. Right, so this is the value of R from there to there. Let's try and find that out. So that distance here, how are we going to find that? Well, you know it's 0.5 from there to there. we can actually use the length of the thread to work out this little bit of distance here, there to there. Let's call this x, which will be the same as this one over here. There's x there. So the value of r will be equal to the 0.5, yes, plus x. So plus x, which is therefore r is equal to 0.5 plus 2x from there. Yes, and then let's find out the value of x. We can use Pythagoras. Well, not Pythagoras. We can use trigonometry again, but using the length this time. So using the length, I'll just draw this triangle over here. So there. This is 1.8 meters. And then we know this is x. And it's still 1.5. Let's try and do this then. So we're just working this out. Then this is going to be sine, yes. So it's going to be 1.8 sine of the angle open bracket 1.5. That's going to be equal to x. Yes, 1.8 times by sine of the angle 1.5. So 1.8 sine of the angle 1.5. My answer is going to be equal to x will be equal to 0.047. 0.047. That's going to be this bit over here. There we go. Right, so the value of r will therefore be equal to 0.5 plus 2 times by 0.047. Yes, so my value of r is going to be times by 2. Yes, plus 0.5. Yes, the answer is going to be r is equal to 0.59 over here. 0.59 meters. So that's my value of r. Right, so now we can do it then. So now we've got the value of r. We can then whack it into this formula. So the value of q. So rearranging this then, q will be equal to whatever this value is. Let's just, I'll put it down as 4.619 times by 10 to the minus 4. Yes, and then I'm going to times it by r squared. R squared is 0.59 squared. Dividing that by the value of k, which we said was 9 times by 10 to the power of 9. And I'm going to square root the whole thing over here. So that squared times by 4.619 times 10 to the minus 4 divided by 9 times 10 to the power of 9. Square root the answer. Yes, I'm getting the answer of q being equal to 1.35 times by 10 to the minus 7 coulombs, everyone. And look, the question was proving that prevate is 0.1 microcoulombs. Don't forget, 0.1 microcoulombs is the same as 1 times by 10 to the minus 7 coulombs. And yes, look, everyone, we have now done this difficult problem. It's a challenging problem because you've got to combine your knowledge of Coulomb's law, which you've just covered, and equilibrium of forces together. And yes, there's trigonometry, and everything is quite synoptic, and everything's being stuck together. So you've got to be able to link the learning yourself. Right, we'll leave it here for today, everyone. If you still like my videos, make sure you subscribe, and everyone, check out my full playlist on this topic to help you with your studies. Ciao, ciao, and goodbye. Comment below if you get stuck, and I'll do our best to solve all your problems. Ciao, ciao. Bye-bye.